Mazes in Python Part 2, Storing and Solving. If you're up for a little challenge and would like to take your programming skills to the next level, then you've come to the right place. In this two-part video course, you'll practice object-oriented programming amongst several other good practices while building a maze solver project in Python. In the first part of this course, you learned how to use an object-oriented approach to store the maze and how to visualize it using SVG. In this second part, you'll complete the project. You'll learn how to define a specialized binary file format to store the maze on disk, transform the maze into a traversable weighted graph, and use a graph search algorithm in the NetworkX library to find the solution. To get the most out of this course, you should have completed Part 1 on building and visualizing the maze, as this course will build on the code and project structure created in it. Don't forget to download the course materials and make use of them. There are a number of mazes included which you'll be able to use when you've completed the maze storage code, and the completed code is always a useful resource. If you get stuck, you can compare your code with the final code to see where an error is. Any code you see running in the REPL will be using the bpython interpreter. This is a replacement Python interpreter that offers a number of enhancements, including code highlighting and suggestions, but any code you see running on screen will work in the standard Python REPL, which is typically accessed by typing Python or Python 3 at your terminal or command line prompt. So now you know how you'll be completing your maze solver project, let's get started. Load the maze from a binary file. After completing Part 1 of this course, you can build and draw the maze. However, creating it by hand in Python takes a lot of error-prone and tedious effort. By the end of this step, you'll have a custom file format for the persistent storage of mazes, which you'll be able to save and load at the push of a button. Besides that, you'll also be able to load the sample mazes supplied with the course materials. Squares in the maze are very much like pixels in an image. One of the sample mazes included in the supporting materials has several hundred of them, but you could very easily be looking at thousands of squares in some larger mazes. If you were to represent the squares as text, then they would quickly amount to a huge file size. Given that you already devised a compact representation for border patterns that leverages a bit field, it makes perfect sense to define a binary file format instead. When defining a binary file format, the first thing you need to decide on is whether you'll store values that can fit in a single byte or more. The reason is that different computer architectures have different endianness, which is a fancy way of saying that they read a sequence of bytes in the opposite order. The two standards for byte order are called big endian and little endian. In big endian, the most significant byte comes first, while in little endian, the least significant byte comes first. If you wrote a numeric value using one standard, but read it with another, then you'll get a garbled result, just as if you applied the wrong character encoding. You're going to need more than one byte to store values like the width or height of the maze, which can be far greater than the maximum byte value of 255. Because many popular file formats stick with the little endian standard, so will you. Binary files often begin with a fixed sequence of bytes to uniquely identify their particular format. For example, Java's class files always start with a 4-byte scene on screen, which is one of the geeky references to coffee in the language's vast ecosystem. Such an initial value is known as the magic number, although it can sometimes be textual. Tools like the Unix file command leverage known magic numbers to detect file types. In this case, the tool correctly recognized an SVG graphics file and the contents of a TOML file as ASCII text. You can choose any magic number for your custom maze file format, but in this course you'll use the 4 ASCII characters maze in uppercase. Their hexadecimal representation seen on screen looks less coffee-like, but it's just as unique and recognizable. The magic number is usually followed by a file header which provides useful metadata about the actual data in the file. The header has a fixed structure consisting of fields, such as the width of the maze. However, the header may have a variable length, for example due to enemy positions kept in a lookup table or other optional fields. If you foresee introducing breaking changes to your file format in the future, for example due to new features, then you should consider including a version field either at the beginning or before the header. This should enable you to handle slight differences across file format versions. Each header field must have a known type, size, and offset measured in bytes since the beginning of the file so you know where the next field begins. The maze header file will have the 3 fields seen on screen. The first field is a single byte with the file format version, which you may increment by 1 with each new release. Notice that the version field starts with an offset of 4 bytes because the magic number occupies the first 4 bytes in the file. The other 2 fields are unsigned integers taking up 4 bytes each, which means they can have values between 0 and over 4 billion, which should be enough for anybody. Once you get through the header and have complete information about the amount and layout of the data, you may start reading the file body, which is the main part of the file. It's where you'll find most of your data, and in this case, the body will be a very long one-dimensional array of numbers representing the various border patterns around the squares and their roles. Now that you've seen how the maze data can be represented in a binary file, in the next section you'll look into packing the data of the file body using as few bytes as possible. Choose your data alignment. Although each border pattern can be defined by as little as 4 bits, because there are 16 different combinations of border sides, you'll need to use the whole byte with 8 bits to represent a border. That's because a single byte is the smallest unit of information in the digital world. It's the same story with your square's role, which would require only 3 bits to describe the 7 unique values. In total, you really only need 7 bits per square to faithfully represent all possible combinations of borders and roles in your maze. Now, it's entirely up to you how you want to align data comprising the square's border and role. If you don't mind being a little wasteful, then one way would be to keep those 2 pieces of information as a binary word made up of 2 consecutive bytes. However, that would effectively allocate more than twice the storage space necessary. A far better option is to fit both numbers, which correspond to borders and roles, on a single byte. You can do this by shifting the bits of one number a few places to the left and computing their bitwise union with the other number. Here, the roll number's 3 bits are followed by the 4 bits of the border number. When you look at the resulting bit pattern from its right edge, you see that the first 4 bits are the same as the bits of the border. The next 3 bits to the left come from the roll. Finally, the most significant bit remains unused, so its value will always be 0. Despite using plain integers in this demonstration example, you'll get an identical result when you place them with your border and roll enumeration members. One crucial difference is that you'll have to explicitly refer to the value attribute of the border or cast the border to int. Otherwise, Python would interpret this last line of code as an attempt to make a compound border member instead of an integer number. The underlying enum int flag data type overwrites the bitwise OR operator to mean something other than its usual definition. The combined border and roll is your square value, which you'll keep in the array of numbers in the file body. You can decipher the border by superimposing a bit mask on top of the square value to isolate specific bits. To get the rollback, you'll use the bitwise right shift operator, which brings the bits shifted earlier back to their original position. Here, the bit mask lets you extract the 4 least significant bits from a number while disregarding the bits to the left. Note that you can express the same bit mask in different number systems. It's customary to use the hexadecimal system because it's usually the most compact. You can see the binary, hexadecimal, and decimal equivalent of the mask on screen. Finally, you can pass the extracted numeric values to the relevant class constructors of your enumeration types. You've just defined a custom binary file format that will allow you to share your mazes with friends or keep them on disk to yourself. As you can see, there's a lot to consider when designing a custom binary file format. Fortunately, all of that is behind you now, and it's time to start digging into the implementation. Make a new Python package called persistence with the 2 files seen on screen inside it. The file format module will contain your file header and its body, while the serializer module will provide the loading and saving routines. Next, you'll need to define Python classes to represent the file header and body, and that's what you'll be doing in the next part of the course. Define the file header and body. Remember that the header follows the magic number, which uniquely identifies your file format. To avoid hard-coding literal numeric values, it makes sense to keep your magic number in a Python constant, which you can refer to by name. You can define the magic number as a read-only bytes object in Python by prepending the letter B to a string literal. Even though a bytes literal looks similar to a Python string, it's actually a disguised sequence of integers in the range of 0 to 255. The letters get internally turned into their ASCII codes. Because you can only use ASCII characters in such a literal, it may sometimes be more convenient to encode them with hexadecimal notation as an alternative. In general, dealing with bytes instead of characters is preferable when you work with binary data. The file header is perhaps best modeled as a Python data class, letting you declare the fields and their types in the expected order. This definition closely follows the table that you saw earlier on in the course, which is shown now as a reminder. These are 3 mandatory fields in the header, all represented as integers in Python. A file header object should be capable of writing its own content into a supplied binary file. You can use the standard library struct module to tell Python how to serialize the individual fields as C data types. You start by dumping the bytes of your magic number and then proceed to write the remaining fields using types encoded with a special format string. The uppercase letter B stands for unsigned byte, which agrees with your expected version field. The less than symbol indicates a little-endian byte order. The number that follows communicates how many consecutive values of the same type you're going to provide. Finally, the uppercase letter I denotes a 32-bit unsigned integer type. So the string means two unsigned integers, one after another, in little-endian order. It makes sense to group as many fields together as possible to limit the number of expensive system calls that write a block of data to the file. Reading back the header from a file is fairly similar to writing it, just in reverse order. At the time of reading the header from a file, no class instance exists yet, so you must define a class method that can act on the class rather than an object. These lines read the number of bytes equal to the length of your magic number and compare the result with a constant. Any discrepancy will stop further processing by raising an exception to indicate an unknown file format. Here, you read a single unsigned byte and assign the result to a local variable with the file format version. Note that there's a comma right after the variable declaration, which is mandatory. Because struct unpack always returns a tuple, even if it only has one value, the comma helps unpack the first element from that tuple. This reads 8 bytes into two unsigned integers in the little-endian byte order. The resulting tuple is then unpacked into a matching number of local variables with the assignment operator. Finally, the method returns a new instance of the file header class initialized with the local variables. Note that your file header is currently version agnostic, so it should work with multiple file format versions. Sometimes you'll want to read only the metadata from the header despite not being able to process the file's body due to an unsupported format. When you finish reading the header, you'll know how many squares there are and how they're arranged in rows and columns. This will allow you to interpret the remaining part of the file correctly, which you'll do next. The file body is less exciting than the header because it's merely a stream of small integers representing border patterns and the square roles in the maze. It might be your first instinct to put them in a Python list or tuple, but the array module in the standard library provides a much better suited data type for efficiently storing such homogeneous numeric sequences. Lists and tuples are heterogeneous, meaning you can stuff elements of all kinds into them. But the price of that versatility is they take up more memory and are slower to access than an array. Because you'll be storing plain numbers instead of Python objects in the file on disk, you can take advantage of a faster and more suitable array data structure, so that's imported first. And then the new file body class is added at the bottom of the file. When passing an array instance to the file body object, you'll need to ensure that the array was created with the right type code that identifies the underlying C type. Here, you use the uppercase letter B to mean an array of unsigned bytes. You'll do that right before reading the file body. To read the body, you must have read the header before so that the internal file pointer is at the right offset. Besides that, the header object is one of the parameters expected by this class method. You use the information stored in the file header to calculate the number of remaining bytes to read by multiplying the width and height of the maze. This data is then converted to a byte array and passed to the file body instance. Writing the file body becomes more straightforward when you call the arrays toBytes method, which takes care of serializing the items to the correct data type in the requested byte order. However, the byte order becomes irrelevant when your array contains only single byte values. Later, you'll use the numbers stored in your array to create border and role instances just like you did before. So now you can individually write and read the file header and body, which are low-level details of your custom file format. but you still need to serialize and deserialize the higher level maze object to allow it to be stored in the file. And that's what you'll be covering in the next part of the course, starting with serializing the maze. Serialize the maze. Unless you already have some data to work with, you're better off implementing the serialization code first, which will eventually write a file that you can later use to test the loading procedure. Open the Serializer module and type the code seen on screen. First, the needed imports are performed. Here, you define the Serialize function, which accepts an instance of the maze model that you implemented in Part 1 of the course. This function produces a tuple consisting of the file header and body, which you'll later dump into a binary file. This prepares the file header by setting a known file format version based on a constant, as there's only one version currently supported. Other header field values are copied from the maze object that was passed as an argument. Here, you populate the file body with binary values obtained by compressing the border patterns and square roles into a single byte for each square. Calling map on the maze instance implicitly iterates over it and applies the compress function on each square of the maze. These lines define a helper function, which takes a square instance as an argument and returns the corresponding role and border values encoded as a compound bit field. It uses bitwise operators to compress the two values into a single number. Writing the header and body to a file is pretty straightforward thanks to the pathlib path object. However, it's important that you open the file for writing in binary mode to ensure that Python writes your data as is without any implicit conversions. With these three short functions, you can now take your miniature test maze that you created in Part 1 and try dumping it to a file. This should create a new file named miniature.maze in your current working directory where you started your Python REPL session. If the file already exists, then it will be overwritten without any warning, so be careful. To quickly verify that the file was created, head over to the file manager in your operating system and look for the new file, which should be 25 bytes in size. The first 13 bytes of the header, followed by 12 bytes corresponding to the 12 squares in the maze. If you have access to a hex editor or a tool like hexdump, then you can inspect the file's binary content, which should look as seen on screen. The first column is the hexadecimal offset of the first byte in each line, which shows the next 16 bytes of the file in a 2-digit hexadecimal notation. For example, the byte at offset 0 is 4D in hexadecimal or 77 in the decimal system. This corresponds to the uppercase letter M in ASCII. On the right, you see a text representation of the same data. The dots represent non-printable characters. Other characters depict bytes that happen to have a visual representation in ASCII. If you discard the header, you'll be left with the last 12 bytes of the file, which translate to the values seen on screen. The resulting sequence of numbers consists of bit fields that should match the squares in your miniature maze. The two outliers with noticeably higher values, 60 and 37, contain extra information about the special roles of these particular squares. In this case, one must be the entrance and the other the exit. However, you can't know that for sure yet because you haven't implemented the maze deserialization code, and you'll fix that in the next part of the course.